All right, so let's begin. So today's presentation is on the high-frequency trading ecosystem, or HFTE. We will introduce the model, and we will also discuss some of the current open problems with the research. In terms of scope, I will discuss some relevant topics. So many of the mathematical models used within the HFTE are usually not used in quantitative finance, but they're more within the world of the applied mathematical and computational sciences as applied to biology. So I will make a small summary of 4 relevant topics which are quite relevant to the HFTE. Then we will introduce the high-frequency trading ecosystem by the means of the high-frequency financial funnel. We will see how the high-frequency financial funnel models some of the classic high-frequency strategies. Then we will take a look at genetic algorithm as a mean to record the dynamics of this ecosystem through time. And finally, we will conclude with some simulation and some of the open problems that I mentioned earlier. So let's begin. In terms of inspiration to other fields. So this is a small cloud of some of the topics that will be involved in this presentation and the next one. Initially, that specific video was meant to be titled Challenging the Accepted Views of Pattern Recognition at Low and High Frequencies. So I decided then to split these two topics into 2 different videos because I thought it would be easier to handle the content of both of these videos independently. So in this cloud, I guess everything but statistics of order and apophenia will be discussed today. So if you're not familiar with some of these words like predator-prey models or neural networks or game theory, then don't worry about it. We will discuss them later. So in terms of providing a background on order books, so an order book is usually a way to organize exchanges between market participants. The way it is usually done, there are different ways to do it. There are actually some interesting things going on in the world of stable matching, which I can discuss later as well. But the classic way to view of the way order books are set up is the following. So you have a bid side here, and you have the ask side right here. And essentially what you do is that you put a bid order here, or a ask order here, or a bid order there, and you also associate the volume that you want to your order to be at and the specific price. And what happens is that the best bid and the best ask takes the priority when there's a match in the agreed prices. If there are 2 market participants with the best price, with the same price, sorry, then the time at which the order came takes the ascendant on the matching algorithm. Okay, so this is very classic up to here. The only small thing that I will be assuming with in the context of this specific presentation is that anything beyond the a 5 depth sort of level in here or in there is reallocated on the 4th layer. Okay, that's the only difference that you have compared to more classic I guess order books. So this is a small caveat. This is a pretty simplistic way to see matching through the world of high frequency trading, because there's actually a lot of exchanges and you can actually beat the system by having a technology which is quite efficient, quite fast. There's all sorts of things that you can do to make money, which will not be discussed today because the concepts that are introduced within this presentation are better understood if you take these small assumptions. Right? You'll understand what I mean as we go more into the model itself. So in terms of providing a bit of background on network topology, so these are the four I guess the four different fields within biology which are not usually associated with quantitative finance. So we'll go through them one by one, but quite rapidly though. So because I want to keep this material quite short, because they're quite straightforward. So first of all, in terms of network topology, you can represent a linear regression through that specific structure here. So this specific network has the potential to create a separation, a linear separation, for example, buy or sell. And why I'm showing this is because in the world of neural networks, in the 60s, it was shown that very simplistic functions like XOR functions could not be modeled through that kind of topology here. So what happened is there was a loss of interest in the field for almost a decade, until it was shown that you could model the XOR function by adding here a hidden layer. Okay, so you have a hidden layer in here, which allows you to create additional separation in this area and then allow you to model the XOR kind of function. So why I'm saying this, you will see that the XOR function is actually quite important in the world of high frequency trading, and you cannot model this if you don't have a topology, a neural network topology, which allows you to model the XOR function. Now, in terms of cellular automatons, if you're familiar with Conway's Game of Life, so you can skim forward, but if you're not, you can, I guess, listen. But the best thing to do is actually, I invite you to Google something like Epic Conway Game of Life simulation to see how incredibly interesting that specific field of cellular automaton can become. Incidentally, Conway is not very proud of his work, whereas it's his most I guess appreciated work that he's done. He's a great mathematician, but it seems like he's not very quite keen on that specific Game of Life. But anyways, in terms of providing you with the 101 of what the cellular automaton does, imagine you have a huge screen, and this could be your screen. This screen has pixel in it, so each little square corresponds to a pixel, and this pixel can be activated or deactivated based on 4 rules. So you have the 4 rules in here, summarized in here. So the first rule that you can see here is death by loneliness. So if you take the reference, this red cell here, if this red cell is in this setup in which there's only one adjacent pixel which is activated, then you have death by loneliness in the next iteration. Then you have death by overpopulation if you have this setup. You have reproduction if you have this setup, and you have no changes if you have this setup. What's interesting again is that by these very simple systematic rules, so you can think of how systematic trading could also be simulated through simple means, but which could have very complicated outcomes, which is what Conway's Game of Life has as an outcome. So in terms of some of the forms that are created as a result of these very simple 4 rules, you have stable forms in here, like the block, the beehive, the loaf, the boat, and you have oscillating forms. So think about these keywords here, oscillations and stability. You can see how the concepts of financial system being stable or oscillation or fluctuations in the financial industry can be induced by similar kind of means. So this is a simple simulation of that specific system. But again, I invite you to just Google epic game of life simulation to see some of these forms. It's just interesting to see for yourself. The third point in mathematical biology that we will discuss is the Lotka Volterra three-species predator-prey model. So imagine you're in an ecosystem of sharks, tunas, and small fishes. You want to model the frequency of their population within this ecosystem through time. And one way to do it is to assume that small fishes grow exponentially in the absence of any predators. So X here represent the small fishes, okay, small fishes, and however their population decays when the frequency of tunas increases, and the tunas in turn are eaten by sharks, which are represented by the Z parameter. So this simple way to represent this ecosystem has great values in the world of mathematical biology, because you can study the stability of that that ecosystem through time by studying that specific matrix J. In terms of having a visual of what I mean, so if you were to, for example, plot the frequencies of, again, X here in blue are the small fishes, red here is the intermediate predator, which is the tunas, and in black here you have the sharks, okay? And in the dark black line here you have X plus Y plus Z. So the dark black line corresponds to more or less the health of that ecosystem. So if you have a lot of different live species in that ecosystem, then you're in here, and if you don't have many, then you're there. Okay, so you can study the stability of that thick line by studying that J matrix that we discussed. Intuitively, you can already see how if you were to be in an ecosystem of strategies composed of high-frequency traders which have like systematic strategies, then you could perhaps come up with similar means of studying the market than the one I just showed. So now, what's evolutionary game theory? If you're familiar with Martin Nowak's work on evolutionary dynamics, then you can again skim through that specific slide, but for those who are not, basically evolutionary game theory is a field which more or less was popularized by Axelrod and its seminal paper on the evolution of cooperation. So the takeover of that specific paper is that if you were to play the prisoner's dilemma one time with someone, then by expectation it's always better to deceive that person. However, if you take an iterative settings, then what happens very quickly, you have a lot of interesting things that emerges. Axelrod himself organized a tournament of algorithms, and he showed more or less with some sort of caveat that the tit for tat strategy is a strategy that is prevalent in that specific ecosystem that he studied. So what Martin Nowak did is that he came with different ways of representing these strategies. So you have in here the prisoner's dilemma summarized. You have the tit for tat strategy payoffs summarized here. And here you have some probabilistic representation of different strategies which are quite popular. And noticeably 4 different strategies which are quite important in what I'm trying to convey here is the first one, all C. So imagine a strategy which always cooperates. This strategy invites for the invasion of actually all these. So the best way to see this is through that war and peace chart. So in here, I'm focusing on this area. This blue arrow here means all C's, so a strategy which is all C invites the invasion of the strategy all D. So all D meaning always deceit. Okay, but what happens here is that if you come up with an ecosystem which allows for mutation, then the all D would invite strategies like the tit for tat. So the tit for tat, what it does is that it always cooperates on the first step, but what happens is that if it sees that the opponent is deceiving it, then it deceits. But it also has the ability to forgive, which is one of its nice features. And the idea is that if there's enough tit for tats in that ecosystem which can help each other, then the tit for tat strategy can invade all the ecosystem. Okay. Then other things can happen. For example, here the tit for tat itself can be theoretically invaded by the generous tit for tat, because some misunderstanding between two tit for tats can induce an infinite series of cooperate and deceits in alternates, whereas the generous tit for tat forgives for one deceit. So theoretically, the generous tit for tat could invade the tit for tat strategy. Now that we have seen these four key subfields of mathematical biology or computational biology, if you're more into computer science, let's start with the high-frequency financial funnel and the HFTE model in general. So what's the high-frequency financial funnel? The high-frequency financial funnel is a network topology or a neural net which is composed of 9 entries and 3 hidden layers and 1 output layers. Each layer is connected to the next and to itself. And the best way to actually see what I mean is to take a look at the picture. Okay, so you have the input layers here, you have the hidden layers there, you have the output layer there, and in here, the 9 inputs that you have, notice the colors. The colors are actually there to symbolize the colors from one of the very first slides that we saw on the order books. So you have the bid ask, the bid and the ask side there, with the differences in the volumes of the different points of the order book, with again the small changes here in which you add the volumes of the areas of the order books which are more deep than the fourth layer. Okay, take a look at that slide on the order book if you want to see the direct mapping. It's with the colors, it should be straightforward enough. So in here, each line that you see here represents a weight. So this area, the weights are going between -1 and 1. And every time you see something like this, it's a weight to itself. So these lines, which are to themselves, are distributed between 0 and 1. And here, the output layer represents the execution strategy per se. So that high-frequency financial funnel takes in information from the order book, analyzes it with respect to the weights that I just described, and depending on how high the output is with respect to its own path, then it puts it at different places of the order book. So how is the high-frequency financial funnel model classic financial strategies? That's what we're going to be seeing next. So the first 101 strategy that people encounter when they get into trading is the celebrated trend following strategy. So the trend following strategy can be modeled in very different ways, but one easy way to represent it is through the exponential weighted moving average equation that you've all seen. And the claim is that the high-frequency financial funnel can model such kind of strategies. So you have the proof there, but I don't like convoluted mathematics on slides, and I like big, nice pictures. So let's take a look at this very nice picture. So in this picture, all the weights that are not significant, so very close to 0, have not been represented. So all this area which had a lot of weights and all this area which had a lot of weights has been deleted. Okay, the only relevant thing is this one. So this represents the feedback given by lambda to itself. So you can take a look at the previous slide here. That represents that area here. This area there. And so the high frequency financial funnel can obviously model trend following strategies. So one caveat here I wanted to make: when you talk about these different high frequency financial funnels, then there are different ways to represent sometimes the same thing. So for instance, this is an example of another trend following strategy, a trend following strategy in which you could have differences of trends, or you could split the same trend in two different ways. You could also have one in which this is not there, but the weight is here. That would represent the same thing. So you delete this and this. That would represent the same thing. So there are different ways to represent the same strategy. But the point that I wanted to make is that the high frequency financial funnel can model trend following strategies. So the 102 kind of strategies that is usually seen in quantitative strategies is the celebrated multilinear regression. The claim is that the high frequency financial funnel can model the multilinear regressions. And again, if you want to take a look at the proof, you can take a look at the proof here, or you can take a look at the picture. So in here you could see the betas, beta 1, beta 2, beta 3, 4, 5, up to beta 9 here. And these betas would correspond to the beta that minimizes the error squared from the multilinear regression, which is given here. Okay, so these are the beta matrix that you get from the multilinear regression. Obviously, you have to select the betas that actually model the error squared of the multilinear regression, but the claim is that you can do it through this specific topology. So similar to what I mentioned earlier with trend followings, there are different ways to represent multilinear regressions with the high frequency financial funnel, and here's another way of doing such thing. Now we discussed the XOR rationale in one of the slides in which I was introducing the concept of neural net and how you need a hidden layer to represent an XOR. And I mentioned that the XOR strategies, the XOR function is quite relevant for high frequency financial strategies. So one way to see this is through the concept of open interest, which is the total volume left on the order book. Then if you work in high frequency trading, then you know that essentially when the price are rising and the open interest are rising, then you should buy, and then you have the 1 0 0 1 of the XOR function that can be represented this way. The claim is again that the high frequency financial funnel can model such topologies, and you can see through that specific picture that it is the case. You can actually try it for yourself. You'll see that that specific topology can lead to an XOR kind of function. And again, there are different ways to represent an XOR strategy through the high frequency financial funnel, and that's one of them. But if you want to think of another one, just think about all these weights going into this one instead of this one, and having a weight there and not this one. Then you would have pretty much the same equivalent potential for learning the same function. So now we've seen that the high frequency financial funnel, which is that specific topology, is able to model most high frequency financial strategies. Now let's see how we can study the ecosystem of strategies through time. So in order to do this, let's think about a micro increment as an infinitesimal increment of the order book, in which a strategy takes in the information from the order book, analyzes it through that specific high-frequency financial funnel topology that it has, and which is its own, and then outputs an order to the market, which comes and changes that order. So that's a micro iteration. In terms of macro iteration, that's what I call a generational increment, in which after a certain amount of time, then there's a fitting function that kicks in and that looks at the ecosystem, and the successful strategies are allowed to live through an additional generational increment, and the bad ones die away. Okay, and you can represent by NK the total number of strategies in which you have trend followers, multilinear regressions, XOR strategies, and unclassified strategies here. So I will talk about classification a little bit later, but one of the open problems right now is actually to classify these strategies into families. So again, I will discuss this later, but in terms of keeping intuition high, let's assume for now that we have a perfect way to classify these different topologies into families of strategies. Okay, so a strategy again is a structure which is a function of a P&L. So P represents the P&L, T represents the topology or the high frequency financial funnel, its high frequency financial funnel, and O represents the order book, a history of the order book that he has and the current order book. So how do we define the birth and death process in this genetic algorithm? So one way to do this, I mentioned a fitting function earlier. A very simple fitting function is to basically say that I will rank strategies with respect to their P&L. So with 0 being the threshold of survival. And so all these strategies here, which are below that 0 P&L profit and loss threshold, die away. And within the ones that survive, so in here in blue, you have the survivors. Then you split the survivors again into two groups. You have a group A1 and a group A2. So the group A2 essentially only survives, but it's not proficient enough to be allowed to reproduce. And the A1 group here essentially not only survives through that generational increment, but on top of that are able to reproduce. So their reproduction then shifts the frequency of strategies that are in that ecosystem through that time. Okay, but in terms of creating these births, you want these births to be very similar to the parents, but also allow a little bit of changes so that you can see an evolution coming up in that specific ecosystem. And that specific process is done through the mutation process. And that mutation process is essentially one in which the weights of that high frequency financial funnel are redistributed with respect to some rules. So the rules is also more or less a qualitative work at this point. So there's a lot of intuition that have been used up to this point. So I'm sure there's a more optimal way to do it. But the way I've been doing it so far is through a simple set of beta distributions, because the beta distribution allows you to make sure that when you are at the boundaries of the weight, so for example, when you're close to 1 or when you're close to 0 or -1, so you can just scale up that specific point to do it for the negative parts. Then you want to make sure that if you redistribute some weights which are close to 1, you do it in such a way that they don't depart too much away from that 1. Okay, but you want to also allow it to move enough so that in the next generation you have a more bell curved feature appearing. So let's take a look at few simulations. So this is one simulation I came up with. Again, there's all sorts of issues around classification which which are open problems at the moment. But again, to keep intuition high, what you can see here in black is the X is the NK. So it's if you remember that specific graph that I had with the Lotka Volterra 3 predator-prey models, you have all of the strategies which are in the ecosystem added together. So the black line represents the health of the market as viewed in terms of an ecosystem. In blue here, you have the trend followers. In green here, you have the multilinear regressions. And in red here, you have the XOR-like strategy. So again, a lot of classification has been done on the fly to fit the model. It's not perfect, but what I'm trying to claim from my studies so far is that essentially there are two different zones that you can take a look at, the zone A and the zone B. And the zone A and the zone B will be represented by this zone here and this zone there. So what happens into these two zones, you can see that the trend followers increase and then start decreasing as a result of the frequency of the multilinear regressions increasing, which subsequently decrease in favor of XOR strategies, and then you have a decay. So my interpretation so far is that the trend following multilinear regressions and XOR kind of strategies behave very much, not exactly like, because there's a lot of caveats here, but they behave closely, or they have some features rather than the Lotka Volterra 3 predator-prey model. So in terms of the outstanding issues, so there's a lot of questions I'm asking at the moment, but I think the ecosystem feature is really the right one to go by. I think if you in biology you model complexity through simple increments, and I don't see much future with the world of quantitative financial strategies. Independent from studying them at the most infinitesimal level, that is at the strategy level. So the same way you had the gene-centered view of evolution, which shifted the understanding of evolution at the individual level. I think if we take the ecosystem point of view, we can understand the market at a much higher depth than we could otherwise. So some of the questions that we have to ask is that how many other strategies are there? Is there more subtle strategies than trend following, multilinear regression, XOR strategies? So for example, mean reversion is another big one in the world of quantitative financial strategies. Is mean reversion within the family of trend followers, or is it something else? Is the parallel to the Lotka Volterra 3 predator-prey model the right one? Can we use the dual biology problem to solve for some of the questions that we have on the stability of the financial markets? Is the network topology that we discussed, the high-frequency financial funnel, is it the right one? Can we come up with something simpler, or does it really have the potential to model most strategies? These are, again, great questions that can be asked. The mathematics of invasion, so that specific topic needs to be formalized more in depth. So for instance, I think it's intuitively you could see how a multilinear regression is strictly superior to a trend followers, because not only it can see the price movement, but it can also see information on the order book that the trend followers doesn't see. So the same way you could see that for the Martins Novak's work on evolutionary dynamics, where you had all C strategies which were invaded by all D strategies. Can we do the same thing with with trend followers and multilinear regression? So for example, again, perhaps it would be better if I illustrate this. So we had this all C which were invaded by all D's, which were in turn invaded by the tit for tat. Okay, can we do something similar with, instead of all C in here, you would have, for instance, the trend followers. For all these here, you would perhaps have multilinear regressions, and for the tit for tat strategy here, can you put XOR strategies? So for this one, for the very first one here, I'm pretty sure it's the case. Again, for the specific reason I've given you. For the XOR strategy, I'm still a little bit confused about it, but I think intuitively the XOR strategy could potentially hide its position better, so that the multilinear regression strategies cannot use their mathematical weaponry to decipher what's going on in the market when you have a lot of XOR strategies. So you could argue that you could have some sort of invasion due to that specific argument, but you need to formalize it mathematically more rigorously. So this is another question I'm asking myself. Other questions that are interesting: can you come up with a strategy which would invade everything at the same time? So you have the concept of a complex food web in mathematical biology, in which, like, for example, an apex predator could feed on different preys. In the model that we have, we don't have such apex predator. The apex predator only feeds on one prey. Could you think of a strategy which would dominate all of the other ones, so through that specific topology? Can you prove it mathematically? Then there are some questions around the SMC. So can you use multi-target tracking to keep up scenarios of that kind of environment through time? This is, in my opinion, this is near to impossible, but I'm happy to keep an open mind on this one. And the last one, which is quite interesting, is the concept of farming. Can you come up with a strategy which is so enlightened that it understands its own positioning through that food web, and it understands that it needs enough trend followers and multilinear regressions in that ecosystem to survive in the long run? Can you come up with a set of combination of weights in the high frequency financial funnel such that you can achieve such goals? Is another question I'm asking at the moment. Right. And finally, there's a conjecture in the area of mathematical biology which states that increasing complexity in the ecosystem leads to its instability. I'm interested to know whether that specific conjecture, which applies to the world of mathematical biology, also applies to the world of quantitative finance and high-frequency trading. Right, so that concludes the presentation of the HFTE. And if you have any questions, feel free to contact me through my contact information, which are at on the first slide, and I'll be happy to address your questions. Thank you very much.